Sí, claro.
Okay, let us start the second day of this section. The first speaker will be Claudia Alcántara. She will speak about the Poincaré problem for foliation on CP2 with a unique singularity.
Okay, thank you very much for the invitation to the organizers for giving me the opportunity to talk here in this Mathematical Congress of the Americas. I'm going to talk about the Poincaré problem for foliations on the projective plane with a unique singularity. This is a joint work with Ramon Ronson-Lavie from University of Toronto. And begin by saying the Poincaré problem say in general. The Poincaré problem as the following. If we have a foliation on the projective plane of degree d with a rational first integral of degree s, then can we bound s as function of d? I'm going to, I will see later the precise definition and some results to know more about this problem. Well, the plan of the talk is the following: to say what is a foliation in the projective plane of degree d, describe the space of foliations of degree d, to say what is the singularities for foliations, and I'm going to define one important invariant. This is the Miller number of the singularity. I like to say something about the leaves of foliations on the projective plane. And we will see some definitions and known results on this problem, the Poincaré problem. And finally, the results and some examples in this case. Well, we begin with the motivation. The motivation to study foliations on the projective plane comes from the study of differential equations, systems of differential equations in two variables, in two dimensions. This system is defined by polynomials p and q. We can write the system like this, or like a meromorphic vector field. This system is defined in the complex plane because we have polynomials p and q. And when we extend this definition to the projective plane by adding the line at infinity, we can define the foliation in the projective plane.
Claudia, más cerca de tu micrófono, por favor.
Ok, ¿aquí está bien? Hola, ¿me escuchan?
It's okay.
Hola.
Muy bien.
Sí, te
It's
escuchamos.
okay?
Te escuchamos.
Muy bien. Y si, can you see the screen, the presentation?
Yes, we do.
Okay. Okay, then we can define the space of foliations of the projective plane of the in two ways. The first one is the set of meromorphic vector fields defined by polynomials p, q, and r, where p, q, r are homogeneous polynomials of degree d. D is the degree of the foliation. And if we take x defined by p, q, r of x, y, z, we can see that the foliation x is equal to fd minus 1 times the radial foliation, where d minus 1 is a homogeneous polynomial of degree d minus 1. This is because this part of the foliation doesn't have direction in the projective space. And the dual way to define foliation is as a one form, omega, defined by three homogeneous polynomials of degree d plus 1. Here the degree of the polynomials is d plus 1, where d is the degree of the foliation. And the polynomials a, b, c satisfy the Euler condition. This is the Euler condition x times a plus y times b plus c times c is equal to 0. And we must take the projectivization of these spaces. Then, as a corollary, we obtain that the space of foliations on the projective plane of degree d is a projective space of dimension d squared plus 4d plus 2. Then every point in this projective space defines a foliation of degree d. This is a very important result in the theory of foliations. Now I'm going to say what is a singular point for a foliation. If we take the point P in the projective plane, this point is singular for the meromorphic vector field X if when we evaluate the point at the polynomials P, Q, R, we obtain a multiple of the point. That means that we don't have direction in this point. Or if we take the one for omega, the point is a common zero of the polynomials A, B, C. Then the singular set of the foliation is the algebraic variety defined by the polynomials A, B, C if we consider the one for omega. And we can define an important invariant of the singularity. For that, we must take the local generator of the foliation around the point P. Then the Milnor number of the point is the intersection index of the curves P and Q at the point. This is the dimension as a vector space of the local ring at the point modulo the ideal defined by the polynomials P and Q. This ideal is very important for the foliation. It is called the singular scheme of the foliation. And we will see later some geometric properties of this ideal. Well, now we can ask how many singularities has a foliation of degree D. This is a very known result that says that the number of singularities depend just on the degree of the foliation. This is the result. If we have a foliation on the projective plane of degree D with isolated singularities, then the number of singularities is d squared plus d plus 1, counting Milnor number. This is a very important number that we will use in the talk. This number, d squared plus d plus 1, where d is the degree of the foliation. Okay. Here we have two examples. The first one is a very famous foliation called Jonolu foliation. This is given by this meromorphic vector field, yd in the direction of x, cd in the direction of y, and xd in the direction of c. This foliation has d squared plus d plus 1 different singular points. That means that every singular point has Milnor number 1, And the second example, for the second example, we remove the last term, for example, xd. We obtain this foliation, yd in the direction of x and cd in the direction of y. This foliation has just one singular point at the point 1, 0, 0. That means that the Milnor number is the maximum. This number is d squared plus d plus 1. You have the two examples. Well, now I like to say something about the leaves of a foliation, leaves of solution for the foliation. In this context, we have also the existence of a uniqueness theorem for differential equations that says that a foliation has a unique solution or leaf which pass through every non-singular point. The leaves are analytic curves always, but in the particular case where the curve is algebraic, we say that the leaf is algebraic. Okay, this is for non-singular point. But what happens at the singular points? Well, we have the following important result by Camacho and Sat, proved in 1982. And the theorem says that for every isolated singular point for a foliation on the projective plane, pass at least one irreducible leaf. This is analytic, okay? Then we have at least one. This is a result in dimension 2. In dimension 3 is not true, this result, for example. Then we can have a finite or an infinite number of leaves through every singular point. In the case where the singularity has an infinite number of leaves, it is called the critical. We will see some examples of this kind of singularities at the end of the talk. Here, just for fun, we have the real picture of the leaves of the Jonolu foliation of degree 3. This is the real picture because the leaves are of dimension real 2, but here we have dimension real 1. Well, now we return to talk about the Poincaré problem. This is the aim of the talk. For that, I like to say what is a rational first integral. Well, a rational first integral of degree S for a foliation in the projective plane is a rational function defined by polynomials f and g, f over g, the rational function, where f and g are homogeneous polynomials of degree S. This is of the foliations are the elements of the pencil defined by f and g. Pencil is a family of algebraic curves parameterized by that. Then every point in the base locus of the pencil, the common zeros of f and g, are the critical singularities for the foliation. Because in these singularities, we have an infinite number of leaves. Every element of this pencil, then we have the critical singularities in this case. And I remember that the Poincaré problem as the following. If we have a foliation on the projective plane of degree D with a rational first integral of degree S, then it's possible to bound S as function of D. This is the problem. The answer of this question in general is that it's not possible, as the following classic example shows. Consider the one form omega defined in this way: P, Y, C, the differential of X, plus Q, X, C, differential of Y, minus P plus Q, Y, X, differential of C, where P and Q are natural numbers. Then this one form is of dimension 2. Then the corresponding foliation has degree 1. It's easy to see that the rational first integral for this foliation is this rational function xpyq over c p plus q. Then this rational function has degree p plus q. Then we can choose S equal p plus q arbitrarily large, but always the foliation has degree 1. Then it's not possible to bound the degree of the rational first integral in this case. And this is a very important problem, the Poincaré problem, that has been studied by many people. For example, Poincaré, Dulac, Painlevé in the 19th century, and in the 20th century by Cerveau, Lisneto, Carnicer, Pereira, Zamora, Esteves. Many people work in this important problem. I'm going to say 3 theorems related to this Poincaré problem. There is in the foliation. First, theorem by Cerveau, and it's a on the plane of degree D and C. It's a reduced nodal algebraic leaf of degree S. Nodal means that we have just not as singularities of the curve, of the algebraic curve. Then the degree of the leaf is less or equal than D plus 2. D is the degree of the foliation. Moreover, if the curve is smooth, the algebraic curve is smooth, and the degree is equal to D plus 1, then in this case, the foliation has a rational first integral. The important hypothesis here is that we have just nodal singularities. The second theorem is by Carnicer. This is a very important theorem in this theory. It was proved in 1994. And it says that if we have a foliation on the projective plane of degree D and C is an algebraic leaf of degree S without the critical singularities, remember that the critical means that we have an infinite number of leaves. Then if the leaf doesn't have the critical singularities, then the degree is less or equal than D plus 2. In our case, we can't apply this theorem because we have the critical singularities. But this is an important theorem if we don't have the critical singularities. This is the bound of the possible algebraic leaf, is D plus 1. The final result that I like to remember is a theorem by Zamora, proved in 1997. In this case, we have the critical singularity. We have the critical singularities. And the result says that if X is a foliation on the projective plane of degree D with a rational first integral of degree S, that means that we have the critical singularities, and every singularity has eigenvalues 1, 1, or minus 1, 1, then 2 times the degree of the rational first integral minus 2 is equal to the degree of the foliation. Here we have a strong hypothesis on the singularities because we ask for linear pair and every singularity with eigenvalues 1, 1 or minus 1, 1. In this case, we know exactly what is the degree of the rational first integral. Okay. Now I like to say what is the principal problem to bound the degree of the rational first integral. Suppose that we have a foliation on the projective plane of degree D with a rational first integral f over g of degree S. Then we know that the leaves of the foliation are the elements of the pencil defined by f and g. This is the family of algebraic curves parameterized by the projective line. There is an important result that says that we have just only a finite set of elements in the projective line such that the corresponding fibers are reducible or non-reduced. just a finite number. Here we take n elements in this set. Suppose that every fiber in this set has this decomposition with irreducible components. U are the irreducible components of the fibers with exponent n. N is a natural number. We have the decomposition of every fiber, and now we take R, the product of all irreducible components with 1 degree less. Here we have degree n, and here we have degree n minus 1. If we take this product, R, and if we consider the 1/4 omega, defining the foliation to prove the following equation. If we take F differential of G minus G differential of F, this is equal to R times the 1/4 omega. That means that if R has degree n, we obtain the following: S, the degree of F, plus S minus 1, the degree of the differential of G, is equal to n plus D plus 1. D plus 1 is the degree of the 1/4. This is equivalent to have 2S minus 2 equal to n plus D. Then the main challenge to solve the Poincaré problem is that it's difficult to know R, the product of the irreducible components of the non-reduced fibers. For that, it's difficult to bound the degree of the rational first integral, because it's difficult to know this polynomial R. But here we can see that always we have that S is greater or equal than D plus 2 over 2. S the degree of the rational first integral. For that, it's difficult to solve the problem, because every pencil has different non-reduced fibers. Well, now I'm going to give the result. We work in the Poincaré problem for a special kind of foliations. Foliations with one singular point, just one singular point. In this context, it's easy to say something about the rational first integral. Well, we are interested in this kind of foliations with one singular point. That means that we have Miller number d squared plus d plus 1. We begin by saying something about this kind of foliations. Well, the complete classification of these foliations is known only for degree 1 and 2. But we can construct examples. It's more or less easy to give examples in every degree. For degree 1, we have Miller number 3, d squared plus d plus 1. And if we fix the point at 1, 0, 0, there is only one foliation with a unique singularity. Only one up to change of coordinates. The foliation is x1 here, y in the direction of x plus c in the direction of y. This is for degree 1, just one foliation. For degree 2, we have Miller number 7. And if we fix the point at 1, 0, 0, there are only 4 foliations with a unique singular point. The first one, x1, y in the x plus c side, it's a foliation with a rational first integral. The foliation x2, x3, and x4 don't have a rational first integral. And there are 4 foliations to change of coordinates with a unique singular point. Well, now to give you the results in this context, but we need to say to some observations. The first one is that
Hello. Some problem?
I think we lost Claudia.
I think so.
I fix.
Yeah.
I hope we didn't lost Claudia, only the connection.
Oh, yes. So I think let's wait a little.
Yes, let us wait. How are you, David?
I'm good. You?
Fine.
We are
we are all in the same boat.
Yes.
She disappeared.
How are things going in Brazil, Ronaldo?
Pardon?
How are things going there in Goiânia?
Fine.
Fine.
Not so good, but we are how to say this? We are surviving
Okay.
in the epidemic. How to communicate with Claudia? It's impossible.
I
I
don't
don't know
know
how
if
to.
maybe someone in Mexico has another way of communicating with her.
By
I'll
phone.
try to.
By phone.
I'll try to get her a way to communicate with her. Wait.
Thanks.
Wonderful.
Hi, Ronaldo.
Hello.
Está lendo seus mensagens do WhatsApp. Eu acabei de mandar um.
Okay.
Acabei de mandar uma mensagem para o WhatsApp, né?
Você não pode comentar nada, você sabe que está tudo gravado, né?
Ontem tive problemas depois da minha palestra da
Eu também
internet.
tive problemas ontem.
Nossa, ainda bem, senão seria igual hoje.
Eu também tive problema várias vezes. Ontem eu tive 3 ou 4 problemas de comunicação. No final, estabilizou.
É, mas no final. Tá bom, já que está.
Hi, sorry.
Come back.
My connection is very, very weak. Sorry. Now I connecting with the phone. Sorry.
No problem. Let's continue.
Can you see the presentation? Could you see the presentation?
Yes.
But before this,
Yes?
we lost
Okay.
before.
Sorry. Before? There?
Here.
Click here. There are four types of.
Four types of degree 2. The next.
Okay. This one?
Yes,
The
exactly.
next. Okay. There?
Yes, it's okay.
Okay. Now I'm going to say the results. Some observations. If we have a foliation on the projective plane of degree D with a unique singular point with a rational first integral, then in this case, because we have just one singular point, the base locus of the pencil has just one point, the point D. This is because every point in this base is a singularity of this set, but in this case, this is the unique singular point because we are asking for this type of foliations. This is important for the geometry of the singular scheme. The geometry is the ideal, the singular scheme is the ideal defined by F and G. Now, this is the first result. This is the following theorem. If we have a foliation on the projective plane of degree D with a unique singular point and with a rational first integral of degree S, then S is less or equal than D plus 1. I'm going to say something, the principal ideas for the proof of this theorem. We must take the local form of the foliation in the affine chart where X is equal to 1, for example. We take the local form of the foliation defined by P and Q. We have a unique singular point at 0, 0, and we have a rational first integral of degree S. The rational first integral is locally defined by the curves F and G. Then we take the defined by alpha and beta, the fiber alpha F minus beta G is a leaf of the foliation if there exists a polynomial h of degree D such that the scalar product of the foliation with the divergence of the fiber is the fiber times h. This is because the divergence is a normal vector curve. Then this is the condition, the algebraic condition to have a leaf, and we can prove, on the other hand, that R times H is the Jacobian of the rational first integral. Fy gc minus fc gy. And with this in mind, for the proof, we use the following facts. The first one is the geometry of the singular scheme of the foliation. The singular scheme is just the ideal defined by the polynomials. The second one is the intersection index of the curves, F, G, R, H. In this case, it's easy because we have just one singular point. Then we use a formula by Ledontan to prove that the intersection index of the fiber with H minus the Milnor number of the fiber at the point is equal to SD minus S minus 1 square. We use also a bound given by +q of the Milnor number of the curve of degree S with a unique singularity. The Milnor number is less or equal than S minus 1 times S minus 2. And finally, this is a very important thing in the proof, we use the Hurwitz formula applied to a morphism that in this case we can define from the algebraic plane curve defined by H to the projective line. In this case, with one singular point, we can define this morphism. But I think that we can generalize this result to try to say something in other kind of foliations. With this, we obtain the bound. Remember, is S is less or equal than D plus 1. The first important corollary of this term is a bound for the Gomez-Mont-Seade-Verhofsky index. This is an important index. It's a sort of Poincaré index for the restriction to the leaf. The corollary in this case says that if we have a foliation on the projective plane with a unique singularity and with a rational first integral, then the Gomez-Mont-Seade-Verhofsky index in any leaf, the leaf of the foliation, satisfies the following: is greater than 1. This is important because Brunella proved that this index for any foliation is positive if the singularity is not the critical. In this case, we have the critical singularities, the critical singularity. And examples where this index is negative if the singularity is the critical. For that is important because in this case it's positive, it's greater than 1, the Gomez-Mont-Seade-Verhofsky index. Okay, this is an important corollary. And finally, I like to give the examples. Before giving the examples, we remember the following. If we have a foliation on the projective plane of degree T with a unique singularity and with a rational first integral of degree S, then we have that S is greater or equal than D plus 1 over 2 and less or equal than D plus 1. We will finish the talk giving examples for S equal D plus 1 over 2 and S equal D plus 1. The first example is the following. Take S a natural number greater than 1 and consider this rational function of degree S given by this quotient. Then it's easy to see that the associated function to this rational function is the differential of the rational function, has a unique singular point, and the degree of the foliation is 2s minus 2. That means that in this case, every fiber of the pencil is reduced because the degree of the polynomial R is 0. We have the bound 2s minus 2, or s equal to d plus 1 over 2, where d is the degree of the foliation. Finally, This is a theorem. This is the description of the space of foliations with a rational first integral of degree d+1 with a unique singularity. This space of foliations on the projective plane of degree d with a unique singular point with a rational first integral of degree d+1 is an irreducible algebraic variety of dimension d+4. This is also a smooth algebraic variety. This variety is given of the change of coordinates by the foliations given by this form. This is the meromorphic vector field where P is a polynomial in two variables. This is a homogeneous polynomial of degree t plus CD in the direction of y, where we have this condition. P evaluated in y0 is different from 0. The proof of this theorem uses geometric invariant theory with the action by change of coordinates in the space of foliations. This is the description. We take the change of coordinates of this space to obtain the dimension 4. And we can obtain explicitly the rational first integral for the foliations in this space. For example, this is a foliation that we saw before, the yd in the direction x plus cd in the direction y. The first integral of this foliation is this rational function x cd minus 1 over d+1 y d+1 over c d+1. This is the rational first integral of degree d+1, where d is the degree of the foliation. And it's easy to obtain the rational first integral for every element in this space. And that's all. Thank you very much for your attention, for your passion with my internet.